Welcome back to the video course on fluid mechanics. So, in the last lecture we were discussing about the dynamics of fluid flow, we are discussing about the energy equation and we were discussing about the corresponding Bernoulli's equations and its applications. So, today we will before further proceeding to other topics, we will be discussing more about the limitations of the Bernoulli's equations, which we have already seen earlier. So, as we have seen here, we have already seen large number of applications of the Bernoulli's equations. So, the general energy equation with respect to the Bernoulli's equations is already we have discussed here. So, it is P1 by gamma plus alpha V1 square by 2G plus E1 plus QW plus HE is equal to P2 by gamma plus alpha V2 square by 2G plus Z2 plus E2 minus E1. So, this we have already seen by considering with respect to two sections of flow between, say for example, if we consider a pipe flow like this. So, we have already seen say here between section 1 and 2 here the total energy equation or general energy equation is written as P1 by gamma plus alpha V1 square by 2G plus Z1 plus QW plus HE is equal to P2 by gamma plus alpha V2 square by 2G plus Z2 plus E2 minus E1. So, here this various terms like QW is the heat added for with respect to system which we discussed. QW is the heat added per unit weight of fluid, E1 E2 are the internal energy per unit weight of the fluid at respective states, and HE is the external work done. So, now here we have already seen this E2 minus E1 minus QW is equal to reversible and irreversible head. So, irreversible head is the head loss. So, HL is the energy loss per unit weight of the fluid due to the friction and other causes. So, for an incompressible fluid flow, the total head at 1 plus head added due to the machine or the head loss is equal to total machine minus head loss equal to total head. So, finally, the general energy equation we can write as H1 plus HE minus HL is equal to H2, and the work done over a fluid is equal to power inputs into power into flow is that is equal to P is equal to gamma QHM in watts, and where gamma is the unit weight of fluid and Q is the discharge in meter cube per second and HM is the head added to the flow in meter. So, we have already seen a large number of applications of the Bernoulli's equation, and now we have already discussed the general energy equations. So, the general energy equation is, say, the Bernoulli's equation which we have derived is for inviscid flow, but that Bernoulli's equation can be generalized with respect to the equations which we have seen as general energy equation. So, now say the Bernoulli's equation which we have discussed have a number of limitations, since we have put certain assumptions with respect to the derivations of the Bernoulli's equation. So, the limitations, the important limitations are, say, first one is the compressibility effects of the fluid. So, the Bernoulli's equation which we have derived or which we have discussed so far, the compressibility effect is not taken into account. So, we have assumed that the fluid is incompressible. So, if the compressible fluids are considered, then we have to slightly modify the Bernoulli's equation. So, the Bernoulli's equation can be modified for the compressibility effects, and then also the Bernoulli's equation which we have discussed so far is for steady state. So, whenever the problems we have to deal with the unsteady conditions, then the equations is to be modified for the unsteady flow. So, in the next slides, so here say with the limitations of the Bernoulli's equation which we have already seen earlier. So, here you can see the the Bernoulli's equation for the say unsteady case. So, here you can see, say, the rho into del V by del T. So, the steady state equation is modified like this: rho into del V by del T ds plus dP plus half rho dV square plus gamma dz is equal to 0 along a streamline, and similarly we can write P1. So, this we can rewrite as P1 plus half rho V square plus gamma Z1 is equal to rho integral S1 to S2 del V by del T ds plus P2 plus half rho V2 square plus gamma Z2 along a streamline. So, say the Bernoulli's equation which we have seen earlier discussed is steady state. So, as shown here, we can modify whenever we consider the the transient or the unsteady conditions. So, these are some of the limitations of the Bernoulli's equation, and further limitations are say like the rotational effect. So, whenever the fluids which we consider has got the rotational effects, so the rotational effects care should be taken while applying for flow across the streamline. So, we have derived the Bernoulli's equation by considering a streamline. So, say whenever the rotational effects are there for the problem which we consider, we have to take care the while applying the flow across a streamline. And also other limitations include the equation, the Bernoulli's equation is not valid for flows with mechanical devices. Say for example, whenever a pipeline system is say when we are considering a problem with the pumps, turbines, etc., we have to take care, special care should be taken so that the Bernoulli's equation is can be applied. And as we have already seen, one of the important assumptions in the derivation of the Bernoulli's equation is fluid is inviscid. So, whenever viscous fluids are considered, still Bernoulli's equation can be applied, but there will be say it is one of the limitations. It is not 100% correct that for viscous fluid this equations say the assumption, the Bernoulli's equation is derived based upon the assumption is that fluid is inviscid. So, these are some of the important limitations on the use of Bernoulli's equations. So, now we will see few of the example problems with respect to the Bernoulli's equations we have discussed so far before going to other topics. So, the Bernoulli's equations, the example number 2, earlier we have already seen one of the examples. So, the next example is, so here we consider a problem, water is flowing through a smooth pipe of uniform diameter. So, here there is a pipe, the diameter is 20 centimeter at section 1 at elevation 5 meter. So, here we consider two sections, section 1 at 5 meter from datum. So, this is the datum, the pressure is 30 kilopascal. So, here the pressure is 30 kilopascal at section 2 at elevation 7 meters. So, here at this section pressure is 15 kilopascal and velocity is 1 meter per second. So, we want to find the head loss between the sections between section 1 and 2 and the flow direction. So, this is one of the simple application of the Bernoulli's equation. So, here a pipe flow is there and then water is going through the pipe and say the velocity is given at section 2 and the pressures are given at section 1 and 2. So, we have to find out the head loss between section 1 and 2 and the flow direction. So, this is one of the simplest application of the Bernoulli's equation. So, to solve this problem, so first we will use the continuity equation. So, if you use the continuity equation, since we are considering two sections, say the continuity equation can be applied. So, with respect to the conservation of mass. So, if you apply the continuity equation, Q is equal to A1 V1 is equal to A2 V2. So, here already the diameter is known. So, the diameter is 20 centimeter. So, Q is equal to pi by 4 into 0.2 square and the velocity V1 is given as 1 meter per second. So, pi by 4 into 0.2 square into 1. So, that gives say 0.0314 meter cube per second. So, here since the pipe is assumed of uniform diameter. So, V1 is equal to V2 and A1 is equal to A2. So, and also the specific weight of the liquid is 998. So, this can be converted say 998 into 9.81 by the rho is given us. So, here the rho is given us 998 kilogram say per meter cube. So, that can be converted as gamma is equal to gamma is rho g. So, 998 into 9.81 by 1000. So, 9.79 kilonewton per meter cube. So, we are considering atmospheric pressure and hence we are taking it as 0. So, at section 1 if you apply the Bernoulli's equation. So, if you consider section 1 here, if you consider the Bernoulli's equation here. So, we can see as per the Bernoulli's equation P1 by gamma plus V1 square by 2G plus Z1. So, P1 by gamma already it is given that the pressure is 30 pascal. So, P1 by gamma is 30 by 9.79. then B1 is given as 1 meter per second. So, P1 by gamma is plus V1 square by 2g plus Z1 becomes 30 by 9.79 plus 1 square by 2 into 9.81 plus 5. So, that will be obtained as 8.115 meter. And then if you consider similar way the section 2.2, so which we consider here. For section 2.2, S2 is equal to the total head S2 is equal to P2 by gamma plus V2 square by 2g plus Z2. So, P2 is given as the pressure is at section 2.2 is given as 15 kilopascal. So, P2 by gamma is 15 by 9.79 plus V2 is 1. So, 1 square by 2 into G 9.81 plus Z2 is 7. So, this we get as 8.583 meter. So, here you can see this S2, S2 is greater than H1 since 8.583 is greater than 8.115. So, flow occurs from section 2 to 1. So, here we can see that the pressure, the head here at section 2 is much higher than section 1. So, that we can say that the flow takes place from section 2 to 1 and the head loss is S2 minus H1 is 0.468 meter. So, like this, so this is one of the simple application of the Bernoulli's equation. We can apply the Bernoulli's equation for a large number of problems. So, we will also discuss few more examples here. So, example number 3 which we discuss is here a tank is filled with oil of relative density 0.9 and a siphon of diameter 10 centimeter is used to empty the oil as shown in figure. So, here this is the figure here. So, here we have got a tank and then a siphon is used to empty the oil from this tank like this using a siphon, and the question is the oil surface in the tank is at an elevation of 5 meter and the siphon discharges to atmosphere at an elevation of 2 meter. Center line of siphon at its highest point D is at an elevation of 6 meter. The losses in pipe to higher point D is 0.7 meter and 0.9 meter from higher point to the outlet. So, we have to find out the discharge in the pipe and the pressure at point D. So, the problem is here we have got a tank and then say we are using a siphon to say take the oil out from the tank. So, with respect to this, here you can see we have to find out the discharge in the pipe through the siphon and then we have to find out the pressure at point D. So, this is the problem. So, here it is given that the density of oil rho is 0.9 and then D is the diameter of the pipe is 10 centimeter. So, if you consider, we will now consider we will be using the Bernoulli's equation. So, here, so we will consider 3 points. One is the liquid level or the oil level in the tank. So, this is 0.1 and then we will consider 0.2 as the outlet of the siphon. So, here this is 0.2 and then we will also consider the highest point of the siphon. So, that is 0.3. So, we will consider these 3 points and then we will use the Bernoulli's equation to solve this problem. We want to find out the discharge passing through this pipe and then also the pressure at this point D. So, this is the problem. So, now if you consider 0.1, we can see that here this tank is open to atmosphere. So, that we can say that the pressure P1 is equal to 0 and then here there is no velocity of fluid. So, V1 is equal to 0 and then the elevation head is given as Z1 is given as 5 meter for this problem, and then at section 2 where at the outlet of the siphon we can see that the pressure is given as P2 is equal to 0. So, that it is say freely flowing to the atmosphere. So, P2 is equal to 0 and then say we can see here the elevation head is given as 2 meters. So, now we will apply initially we will apply the Bernoulli's equations between section 1 and 2. So, if we consider the Bernoulli's equation between this 0.1 and 0.2 here or section 2 and section 1. So, using the Bernoulli's equation we can write P1 by gamma plus V1 square by 2g plus Z1 is equal to P2 by gamma plus V2 square by 2g plus Z2 is plus head loss between say 0.1 to 0.2. So, this is the Bernoulli's equation. So, here you can see that we have already seen P1 is equal to the pressure at point 1 is atmospheric. So, we consider it 0. So, P1 by gamma is 0, and then velocity at this location is also 0. So, V1 square by 2g is 0, and Z1 is already given us 5 meter. So, 0 plus 5 is equal to. So, at section 2 P2 by gamma, P2 is already 0. So, this term also 0, and plus V2 square by 2g. So, here the velocity at this section 2 be V2. So, V2 square by 2g, and the elevation rate is given as 2. So, the plus 2 plus we have got to the head loss. So, the head loss, it is already in the problem, it is already given here. The head loss, the losses in pipe to higher point is 0.7 and 0.9 from higher point to the outlet. So, these are the head loss from say section 1 to 2. So, 0.7 plus 0.9. So, this also added, and then we use the Bernoulli's equation between section 1 and section 2. So, now if we use this say here, and now we can write V2 square by 2g is equal to, we get an expression for the velocity. So, V2 square by 2g is equal to 5 minus 3.6, that is equal to 1.4 meter. So, finally, we get the velocity at the outlet V2. So, here we get V2, we get the value of V2 as V2 is equal to 5.241 meter per second. And finally, in the first part of the question is we want to find out the discharge. So, discharge is equal to area of cross section into velocity. So, area of cross section is the diameter of the pipe is 10 centimeter. So, pi by 4 into 0.1 square into the velocity V2 5.241, that is gives the discharge. So, finally, we get the discharge as 0.0412 meter cube per second. And then the second part of the question here is we are asked to find the pressure at highest point D. So, to find out the pressure at point D, so we will again consider here the figure. We will consider the Bernoulli's equation between say this point section 1 and section 3. So, between this point and this point we will consider between 1 and 3. So, if you apply the Bernoulli's equation, again P1 by gamma plus V1 square by 2g plus Z1 is equal to P3 by gamma plus V3 square by 2g plus Z3 plus HL, that means the head loss between section 1 and 3. So, here you can see that since the pipe, the siphon is of same size, and then say area of cross section is same. So, the velocity also we can see that V3 is equal to V2. So, we have already found V2 as 5.241. So, V3 is equal to V2, that is equal to 5.241 meter per second. So, since uniform pipe section. So, finally, if you write the Bernoulli's equation between sections 1 and 3, we can write 0 plus P1 by gamma is 0. So, V1 is 0. So, 0 plus 5, that is equal to P3 by gamma plus V3 square by 2g. V3 is already found 5.241. So, 5.241 square by 2 into 9.81 plus 6 is the Z3. So, here you can see that this section is 6 meter, elevation is given as 6 meter from the datum. So, plus 6 plus the head loss between say point 1 to 3 is given as 0.67 meter. So, plus 0.7 meter. So, this is the Bernoulli's equation between section 1 and 3. So, finally, we can get P3 by gamma as P3 by gamma is equal to 6 minus 0.7 minus this V square 5.241 square by 2 into 9.81. So, this is equal to minus 3.1 meter. So, pressure at D finally we get this will be P3 by gamma gives the pressure at D. So, that is equal to minus 27.315 kilopascal gauge. So, this is the pressure at D. So, like this say we can use the Bernoulli's equations for a given problem to find the discharge or the pressure or whatever the variable depending upon the problem. So, before closing this, we will see one more example related to the Bernoulli's equation. So, the fourth example related to the Bernoulli's equation is, so here we have got a water tank, and then we use a pump here to pump water from this tank. So, and then here water is pumped from a tank at the rate of 0.5 cubic meter per second. So, here the discharge, the pumping rate is 0.5 cubic meter per second, and the pump supplies an energy of 20 kilowatts. So, here the energy the pump is supplied by the pump is 20 kilowatt. So, we are asked to find the pressure intensity at A. So, A the location of the pump. So, we want to find out the pressure intensity at A. So, here even though there is a pump is attached with the problem pump is there, but still we can use the Bernoulli's equation. So, here first the pump energy is given as 20 kilowatt. So, pump energy is equal to we have already seen the equation for pump energy as gamma q into delta H. So, here pump energy is 20 kilowatt. So, gamma q delta H is 20 kilowatt. So, from which we can write the with respect to the pumping what will be the head. So, delta H is equal to 20,000 by say gamma for water if you take 9,810 and say here the discharge is given as 0.5. So, 20,000 divided by 9810 into 0.5. So, from which we can get delta H, that means the with respect to pumping the head is 4.07 meter of water. So, from that we get the head which can take care by the pump, that is equal to 4.07 meter. And then we have to find the velocity say at say the location A. Here already we have already calculated the head here. So, we from that we can try to find out the velocity. So, already the discharge is given, the velocity at A is equal to discharge by cross sectional area. So, here this pipe diameter is 15 centimeter here. So, from which velocity at A is equal to V A is equal to Q by A. So, we get 28.29 meter per second, and then say if you consider here at the exit of this pipe with respect after the pumping is occurred, here the water is going through this exit at B. So, here the diameter is given as 10 centimeter. So, the velocity at B we can find V B is equal to 15 by 10 square into V A. So, since to conserve the, if we use the continuity equation, we can see that V B into A is equal to say V B into A is equal to A1 is equal to, or A2 is equal to V A into A1. So, if we use this we can see that we can write V B is equal to 15 by 10 all square into V is equal to 63.65 meter per second. So, now again finally we will apply the Bernoulli's equation between point A and C. So, here the tank the top of the water level, here you can see that the pressure will be, pressure is atmosphere. So, we can take it as 0, and then you can see here there is no flow takes place. So, the velocity can be considered 0. So, if you consider the Bernoulli's equation between point C and A, so that we can finally write the equation as say here the Z1 the Bernoulli's equation is applied. So, that gives here the velocity, all the values are known. So, this is 2 plus. So, here you can see that between this level this location A and location C the level difference is 2 meter. So, that we can say that 2 plus so it is Z the location with respect to datum is 2 plus 0 plus 0, since this time the pressure is 0. So, this is 0, the velocity is 0. So, again 0. So, 2 plus 0 plus 0 is equal to P A by gamma plus the velocity here V2 square by 2G. So, that is 28.29 which we already got, or V A square 28.29 square by 2 into 9.81. So, that gives P A by gamma. So, P A by gamma finally we get as minus 38.79. So, here we have seen few applications how we can solve various problems by using the Bernoulli's equation. So, finally, we have already seen say the Bernoulli's equation we are derived by certain assumptions like fluid is inviscid and flow is incompressible, and then we have already seen the limitations, and we have also seen various applications of the Bernoulli's equations, and then we are tried to solve few of the numerical examples. So various typical examples of these kinds of where the Bernoulli's equation can be applied. So we have seen with respect to the energy equations and the Bernoulli's equations, and now we will go to the next topic, which is the linear momentum equations. So here we have already seen the energy equation and then the Bernoulli's equation. Now we will discuss the momentum equation, linear momentum equations. So all these say we have already seen that the Newton's laws we are directly applying. So this momentum, say most of the time, say we will be dealing with so now we are discussing the dynamics of fluid flow. So we are dealing with moving fluids. So all the time the moving fluids exert the forces either one way or another way. So this moving fluids, the force which is exerted by the moving fluids has got a lot of practical importance, where we can use it for various purposes, the momentum or the force created by the moving fluids. So for example, if you consider the lift force on an aircraft by air moving over the wing, and also we can easily see many times say jet action. So many times we use the jet action say for example in turbines and say some of the other kinds of problems where in engineering we use jet action. Say jet means jet. What is jet action? So we will say a fluid is coming through a pipe, and then we are making it just like in a nozzle, we are reducing it say diameter, and then there will be the liquid will be coming at a force to a plate. Here you can see that here there is a plate, so the liquid is coming at a force, and then you can see this is the jet action. So this jet action also, the force is exerted by the moving fluid. So the moving fluids exert forces. So here you can see here there is a nozzle is there, and a jet is put on a say a plate like this, an inclined plate like this. Then you can see that there is a force, and this force is we can utilize the with respect to this force for various engineering purposes. So this moving fluids exert forces, and then with respect to this we can use the momentum equation to find out how much is the force coming. So here we use the Newton's second law to analyze this moving fluids. So we derive the linear momentum equation with respect to the Newton's second law. So linear momentum equation is this momentum equation is statement of the Newton's second law. As I mentioned, say moving fluids exert force. So force is equal to mass into acceleration. So from this the Newton's second law we can derive the momentum equation. So it is actually a statement of the Newton's second law. So if you consider special properties of fluids like relates the sum of forces, we can say with respect to the movement of fluids we can relate sum of forces acting on an element of fluids to its acceleration or rate of change of momentum. So as per linear momentum equation, by using the Newton's second law, we can say that we can write the sum of forces acting on an element of fluid to its acceleration or rate of to its acceleration or rate of change of momentum. So force is equal to mass into acceleration, and then this we can equate to the rate of change of momentum taking place between, say if you consider two section or a control volume, between that control volume what changes takes place, this we can equate to the rate of change of momentum. So that is that way we can derive the linear momentum equation. So from the Newton's second law we can write the rate of change of moment of a body is equal to the resultant force acting on the body and takes place in the direction of force. So this gives the Newton's second law. The Newton's second law states that the rate of change of momentum of a body is equal to the resultant force acting on the body. So using this Newton's second law we can say we can see that here it deals with the system momentum and forces. So if we consider an open system or a closed system, so the Newton's second law deals with the momentum and the momentum occurring with respect to the control volume or the between the sections which we consider, and the forces acting on with respect to the control volume. So both so as we have already seen the control volume concept, so we have to consider the both the forces, the both the surface forces as well as body force acting on the control volume. So control volume, so we have already seen most of the problems which we will be solving here. We are using the control volume. So for the control volume, we have to consider what happens within the body, the control volume itself, and then on the surfaces what happens. So we have to consider, while we consider the linear momentum equation here, we have to consider, we are using the Newton's second law. So force is mass into acceleration, and then we are equating that to the momentum changes. So we have to see the system, the control volume or the system which we are considering its momentum and the forces, and then as the forces or the moment are concerned, what happens on the surfaces as well as the inside or the body forces. So here in this slide, if you consider say a typical control volume for a flow in a tunnel shaped pipe. So this is a pipe coming, and then it is just opens like this, fluid is flowing this direction. So if you want to consider the linear momentum equation for a finite control volume like this, so if you consider section between this section and this section, so we can find out the vector sum of all external forces acting on a fluid mass, and then that will be equal to the rate of change of linear momentum. So as per Newton's second law, we can find out the vector sum of all the external forces, and that will be equal to the rate of change of linear momentum. So finally the linear momentum equation is obtained as we can find out the rate of change of linear momentum. So F is equal to, the force is equal to the vector sum of all external forces equal to dm by dt, or the rate of change of linear momentum. So if you consider this control volume, what are the forces acting on this control volume, and then we can equate the rate with respect to the fluid, say incoming fluid and outgoing fluid within this control volume. So we can find out the rate of change of linear momentum, and then equate to the vector sum of all external forces within this control volume. So now if you, since we are considering here the forces, so when we deal with the forces, any body or any control volume which we deal, we have to deal with the internal forces as well as external forces. So here the forces which we are considering, the external forces which we are considering is, first one is the boundary forces. So what the if you consider the control volume, what are the forces on the boundary, so that includes the boundary forces, and then the normal forces. So with respect to the flow coming inside and flow going outside, there will be normal forces. So we have to consider these normal forces, and then of course the internal forces or the body or field forces we have to consider. So the forces which we have to consider include the boundary forces, the normal forces, and the body or field forces. So these are the forces when we consider the linear momentum equation. So these are for a control volume, these are the forces which we have to consider. So finally, with respect to this, we can write the equation as, so with respect to the Newton's second law, finally the equation can be written here, already shown here. So it is written here. So d by dt, so if you consider the system, integral the system, v rho dv is equal to sigma f system. So you can see the total, the algebraic sum of the forces is equal to the rate of change of momentum. As we have seen, the rate of change of momentum is equal to resultant force acting on the body. So we can write d by dt integral system for the system, v rho dv is equal to sigma f system. So that finally this we can be written as I mentioned, we have to consider the control volume inside the volume what happens, and then on the surfaces what happens. So this term we can write as del by del t of the on the control volume v rho dv plus the control surface integrals the control surface v rho v dot n dA. So, that is on the control surface, that is equal to sigma the forces of the system, that means sigma f contents of the control volume. So, this gives finally the equation which we are looking for with respect to the linear momentum equation for a finite control volume derived based upon the Newton's second law. So, now with respect to the equation which we derived, if you consider here the linear momentum equation for a finite control volume as shown here, say if you consider pipe flow like this. So, on this section we consider two sections. So, here at this section say the area of cross section is A1 and the velocity is U1 and the here the density is rho 1, and then at section 2 if the area of cross section is A2, the velocity is U2 and the density is rho 2. So, force is equal to, as per the equation which we do, force is equal to rate of change of momentum. So, force F is equal to rate of change of moment is given as rho 2 A2 U2 delta T U2 minus at section 2 minus rho 1 at section 1 rho 1 A1 U1 delta T U1 divided by delta T. So, this gives the rate of change of momentum. So, here you can see this is the momentum between section 1 and 2 and the time difference delta T. So, finally, we can write F is equal to Q rho U2 minus U1. So, if we consider this after approximation, after simplification, we can write the force is equal to Q is the discharge passing through this pipe. So, Q is constant, since due to the conservation of mass between section 1 and 2, Q is constant, and if you assume the density rho is constant. So, we can write rho, say rho 2 is equal to rho 1. So, if you consider that, it will be mainly the F is equal to rho Q, capital Q is the discharge, rho Q into U2 minus U1, that means the velocity difference between section 2 and 1. So, F is equal to, the force is equal to Q rho U2 minus U1. So, similarly, so this is if you consider say one dimensional case, and say if you consider two dimensional system. So, we have to consider in x and y direction, and then we have to equate the force in x direction with respect to the change in momentum in x direction, and then force in y direction we have to equate to the rate of change of momentum in y direction. So, similar way we can write for two dimensional system. So, for a two dimensional system, if you consider say the Fx, that the forces in x direction is equal to rate of change of momentum in x direction. So, that is equal to rate of change of mass into change in velocity in x direction. So, rate of change of mass, if any mass change takes place, if you put m dash is the rate of change of mass, and then change in velocity in x direction. So, with respect to this figure, we can write as, so u2 cos theta 2 minus u1 cos theta 1. So, if theta 1 is the angle here and theta 2 is the angle here. So, with respect to the x direction, we can write as Fx is equal to rate of change of momentum in x direction. So, that is equal to rate of change of mass into change in velocity in x direction. So, change in velocity in x direction can be written as u2 cos theta 2 minus u1 cos theta 1 into rate of change of mass. So, this is Fx. So, this finally we can write as, so if u2 cos theta 2 is written as u2x in this direction in x direction, and u1 cos theta 1 is written as u1x. So, finally, Fx is equal to m dash u2x minus u1x. So, that is equal to say m dash say the rate of change of mass, if you write the density into the discharge which flows through the control volume. So, rho q into u2 cos theta 2 minus u1 cos theta 1. So, finally, this can be written as Fx is equal to rho q u2x minus u1x. So, for two dimensional case, we can write in x direction, the force in x direction is equal to the rate of change of momentum in x direction. So, that is Fx is equal to rho q u2x minus u1x. So, similar way we can write for the rate of change of momentum in y direction, Fy is equal to rho q so u2 sin theta 2 minus u1 sin theta 1. So, that is equal to rho q u2y minus u1y. So, with respect to this figure, if u2y is the velocity in y direction and u1y is the velocity for section 1 and u2y is the velocity in section 2 in the direction of y. So, finally, for Fy we can write as that means the rate of change of momentum in y direction is equal to rho q into velocity change in y direction. So, u2y minus u1y. So, this is the case for 2-dimensional system. So, earlier we have seen the case of 1-dimensional system. So, now we have seen 2-dimensional system. So, similar way we can write for a 3-dimensional system also. So, now we have already seen when we discuss the energy equation or when we discuss the Bernoulli's equation or the total energy equation, we have seen that most of the time we will be considering the average velocity. So, with respect to the average velocity, when we consider say for the control volume for the sections which we are considering. So, V is the average velocity as a cross section, but you can see that the velocity is varying from one section to another. So, here you can see that here if you consider a pipe flow here, a pipe flow. So, between section 1 and 2. So, the pipe flow is here. So, you can see that so the velocity variation, if you plot, it will be like this. So, you can see the velocity will be maximum at this center line. So, this is velocity variation. So, velocity will be maximum at the center line of the pipe and it will be 0 on the side wall of the pipe. So, but the equations which we have derived is the average velocity at a cross section, but in actual sense, actually reality, you can see that actual velocity will be non-uniform and it will be, you can see that it will be varying from one section to another. So, as we have already seen in the case of energy equation and the Bernoulli's equation, we have applied a energy correction factor. So, now we are discussing the momentum equation. So, linear momentum equation. So, for the momentum also, since we are considering the average velocity at the section, we have to apply a correction factor, so called momentum correction factor. So, momentum calculated using the average velocity V must be corrected by a correction factor beta. So, here we have to correct the momentum which we have calculated using a correction factor called beta. So, this beta, as we have already seen in the case of energy correction factor, we can in a very similar way we can derive this momentum correction factor beta as beta is equal to 1 by a integral a v by capital V all square, where capital V is the average velocity and small v is the velocity at any section which we consider as shown here. So, this is small v and capital V is the average velocity which we consider for the case. So, beta we have to apply for the momentum equation which we consider, we have to apply a correction factor called the momentum correction factor, and the momentum correction factor beta is defined as beta is equal to if A is the area of cross section, beta is equal to 1 by a integral a upon a v by v all square, where small v is the varying velocity and v capital V is the average velocity which we consider. So, if we consider the flow as uniform flow, then means the velocity is same throughout the section. So, in that case beta will be equal to 1, and then for non-uniform flow you can see that this will be beta will be always greater than 1. So, depending upon the case, say whether it is depending upon the cross section, depending upon whether it is pipe flow or whether it is open channel flow, and this beta will be varying, and whether it is laminar flow, turbulent flow also the beta value will be varying, which we will be discussing later. So, finally, if you apply this momentum correction factor, so to the apply momentum principle to flow through a generalized system, like here you can see the generalized system here we consider. So, here this is the system the control volume which you are considering, and here section 1 and section 2, and here if the velocity is V1 and the discharge passing through the system is Q, and here at section 2 is velocity is V2. So, finally, we have found beta, the momentum correction factor factor we have to apply, and then with respect to this we have to finally we can write the general equation. The generalized equation can be written as sigma f is equal to momentum out minus momentum in. So, sigma that is equal to the algebraic sum of the force. So, see that in the x direction can be written as sigma fx is equal to rho 2 a 2 v 2 into the velocity in x direction vx2 minus rho 1 a1 v1 into vx1. So, in the x direction with respect to this figure, sigma fx is equal to rho 2 a2 v2 into vx2 minus rho 1 a1 v1 into vx1. So, now as we have seen, we have to apply the correction factor beta. So, we have to use the momentum coefficient beta. So, if you use the momentum coefficient, finally the equation should be written like this: sigma fx is equal to rho q beta 2 vx2 minus beta 1 vx1. So, beta 2 is the momentum correction factor section 2, and beta 1 is the momentum correction factor at section 1. So, we can write sigma fx is equal to rho q beta 2 vx2 minus beta 1 vx1. So, this is in the x direction. So, similar way we can write the equation in the y direction. So, like this we can solve the generalized momentum equation is shown here. So, we can use the momentum principle by using the generalized equation. So, as we have seen the Bernoulli's equation, the energy equation, there are large number of applications are there so for momentum equation also. So, here now we will discuss some of the important applications of the momentum equations. So, some of the important applications can be classified like say first one is force due to flow of fluid around a pipe, bench, enlargement and contraction. So, these are some of the applications we can apply the momentum equation for pipe bench, pipe enlargement or pipe contractions. Also in the open channel case also say bends or enlargement or expansions we can or contraction we can use. And second case we can use the momentum equations for force on nozzle at the outlet of a pipe. So, whenever jet action is there we can use the momentum equations, and this is the impact of jet on a plane surface or inclined surface, we can use the momentum equations. And also force due to flow around a curved vane like in a turbine, we can use the momentum equation. So, momentum equation which we have derived or which we have seen so far has got a large number of practical engineering applications. So, we will be discussing some of the applications here, the momentum equation. So, first one is the application momentum equation. First one is force due to flow around a pipe bend. So, here we will discuss a pipe bend. So, say here you can see a bended pipe like this here. So, we want to know how much force is required to force should be there to support, or the thrust block must withstand. So, if there is a thrust block here and then the force the flow is taking place in this say bent pipe. So, we want to find out how much is the thrust block, how much thrust should be put so that we can support the pipe. So, the first application, the force due to flow around a pipe bend, we can solve in the following steps. So, first we will consider control volume. So, we have to consider control volume with respect to flow or with respect to the case which we are considering, and then we will calculate the total force, including the pressure force and body force, and then we can find out the resultant force. So, as we have already seen, as per the momentum equations, we can equate the rate of change of momentum to the force. So, once the force is given, we can find out say the momentum also. So, we can directly apply the case. So, to find out the force due to flow around a pipe bend as shown here. So, the first step is we will consider the control volume. So, here we consider the control volume, that means the section between 1 and 2, we consider the control volume like this. So, this here there is an angle theta with respect to here, and at section 1 the velocity is u1 and section 2 velocity is u2, and x axis in this direction, y axis this direction. So, the total force, which if we consider the total force with respect to section 1 and 2, we can see here in the x direction, as we have already seen earlier, the total force in x direction will be rho q, if q is the discharge passing through the pipe and rho is the density, rho q into u2x minus u1x. So, the velocity in x direction at section 2 and velocity in x direction at section 1 is u1x. So, rho q into u2x minus u1x. So, here if you can see that u1x is equal to u1 itself here, and u2x can be with respect to, if u2 is this direction. So, u2x can be written as u2x is equal to u2 cos theta. So, finally, we can write f2x is equal to rho q u2 cos theta minus u1. So, the force in x direction is equal to rho q u2 cos theta minus u1. So, similarly, total force we can write Fty is equal to rho q the u2y minus u1y. So, in y direction if you consider u2y minus u1y. Rho q into u2y minus u1y. So, here with respect to this figure, if you, since u1 is in this horizontal x direction, so u1 y will be u1 sin 0, that is equal to 0, and u2y is u2 sin theta. So, finally, Fty, the total force in y direction will be Fty is equal to rho q u2 sin theta. So, so we have already considered control volume, and then we have calculated the total force with respect to the fluid movement between section 1 and 2. And then the pressure force, we can calculate the pressure force here between section 1 and 2. So, the pressure force is see the change in pressure force at 1 minus pressure force at 2. So, the pressure force, if P1 is the pressure intensity at section 1 and P2 is the pressure intensity at section 2, we can write the pressure force in the x direction can be written as Fpx is equal to P1 A1 cos 0 minus P1 P2 A2 cos theta. So, here this angle is 0, here angle is theta. So, P1 A1 cos 0 minus P2 A2 cos theta. So, that is equal to P1 A1 minus P2 A2 cos theta. And similarly, in y direction we can write say the pressure force in y direction P1 A1 sin 0 minus P2 A2 sin theta. So, sin 0 is 0. So, this is equal to minus P2 A2 sin theta. And then if you consider the body force, so here mainly it is due to gravity. So, here since the pipe is the bent pipe is put in this way such that the body force we do not have to consider. So, here the gravity force is not considered, body force is 0. So, finally, we can find out the resultant force. So, the resultant force will be the summation of the total force. So, if you consider in the x direction, the summation of total force in x direction, that means rho q u2 cos theta minus u1 plus the pressure force in x direction, so that is P1 A1 minus P2 A2 cos theta. So, this gives the Fx the force in x direction, and then y direction will be Fty, the total force in y direction is rho q u2 sin theta, and then pressure force in y direction is minus P2 A2 sin theta. So, that gives the result, the force in y direction, and finally, Fx is plotted here, Fy is this direction. So, finally, we can find out the resultant force will be square root of Fx square plus Fy square, and the angle will be say Fy divided by Fx, tan phi is equal to Fy by Fx. So, we can find out the resultant force and its direction. So, we have already seen one of the example how we can apply the momentum equation, the linear momentum equation which we have derived. So, how we can apply for a particular case of the force due to flow around a pipe bend. So, what we are doing here is, so we have found the force, the resultant force acting on the particular case, the particular problem, and then so that will be equal to the rate of change of momentum. So, that gives the linear momentum equation. So, using this we can find out the resultant force. So, for this particular problem, how much thrust or how much force should be used if you want to know how much force to support or to put as a thrust block. So, to withstand the pipe. So, that is obtained by the resultant force. So, like this we can apply the linear momentum equations for various cases, and then we will be discussing some few more cases. So, finally, force due to flow around the pipe bend is Ftx in y direction, Frx plus Fpx plus Fbx. So, that is already obtained as Ftx is already found, the pressure force is found, body force is 0. So, finally, this expression gives the force in the x direction, and y direction is Fty minus Fpy minus 0. So, this rho q u to sin theta plus p 2 a to sin theta, that gives the force in y direction. So, we found the force in x direction and y direction, and then we can find out the resultant force. So, that is the thrust required to keep the pipe so that pipe the thrust block should withstand this force. So, this is one of the simple application of the linear momentum equation. So, further we will be discussing some more applications of this linear momentum equations in the next lecture.